So did you enjoy your lunch? Did you enjoy lunch?
Yes.
Okay, good. Yeah. So.
Work because they are sleepy. So
Oh yeah, right. So I'm going to try to inspire you with my talk, innovative approach in memory distillation for enhanced ammonia removal and recovery from wastewater for Texas radio. I think this is my third time to visit CBD. So just a quick quiz before I start my talk. So what is the most famous harbor in Sydney? Darling Harbour, you are from Sydney, right? Yeah. Darling Harbour, everyone knows Darling Harbour, right? Okay. So if you happen to visit Hong Kong, you know the most famous harbor in Hong Kong is, why is that different? Yeah. Are you speaking? Okay. Actually, the name of Hong Kong is called, we can translate to the fragrant harbor. So recently I moved to the university called the Hong Kong University of Science and Technology. And in Hong Kong we have 8 government universities. And Hong Kong University is only one surrounded by a very beautiful harbor. So if you have a chance to visit Hong Kong, I'm sure around this beautiful campus. So I'm leading the advanced membrane for water and energy laboratory in Hong Kong. So our group is working on advanced membrane technologies and also focus on membrane fabrications and also characterization and also the lab to pilot application. So today I'm going to share some of our ongoing work on ammonia nitrogen in wastewater, what are the challenges and opportunities. So first I will introduce the integrate 2 stages of the membrane distillation system for highly efficient ammonia recovery. So the one of the work is the more practical applications, and the second study is the advanced electrochemical MD system for chemical-free ammonia recovery. This is more a little bit more fundamental research. So my talk will be a combination of a practical application and also the fundamental understanding of how can we achieve chemical-free ammonia recovery. Well, you know the ammonia is the second highest produced chemical after sulfuric acid. So the production of ammonia is very energy intensive, and okay. So energy intensive, okay. And also the yearly, the ammonia, the demand of the ammonia is increasing as also the production is increasing. So in order to respond this the energy cost of the high cost of the ammonia production, and also the instead of this the linear line of our economy, which is we produce the ammonia with a high cost, and then the ammonia is turning to the waste. And also we spend a lot of energy and also the cost for just simple end-of-pipe treatment. So that in the end, ammonia is released as the effluent, is no value. So why don't we, instead of this linear economy, why don't you make a circular economy that from the ammonia, instead of just released after the treatment, is there any way we can collect ammonia from the wastewater and then can be used in the circular economy? So this is the starting point of our research work. According to the recent paper, in our, you can see Hong Kong is a very high densely populated area. So So the per person, one day we actually the released about 13 grams of nitrogen, and most of the ammonia through the urine, right, it is collected in the sewage treatment work. So the one of the problem in Hong Kong sewage treatment work is the very high concentration of the ammonia in sludge digest rate. So with the concentration often higher than 500 ppm or even 1000 ppm. So what we do is, because we cannot directly treat this high concentration ammonia, we actually recycle back to the influent. So kind of a dilution. So then it creates a lot of problem that our effluent of ammonia often cannot be the standard. So in case of Hong Kong, what we do is we don't directly discharge the river. We make a deep tunnel and then discharge the harbor, Victoria Harbor. So we need to make a kind of bypass of our the treated wastewater due to the ammonia concentration, nitrogen concentration. So in our study, instead of this end-of-pipe treatment process, why don't we recover the ammonia in the system? In particular, because if we capture the ammonia from this influent or wastewater directly, because concentration is very low and the amount is big. So instead of this wastewater directly, we target the sludge digest rate, because high concentration, the low volume. So why MD? So before I introduce the two-stage process, let me briefly introduce what is the concept of the membrane distillation. So unlike pressure driving process like MF and RO, membrane distillation is we use a hydrophobic membrane. So we create vapor gradient through the temperature differences between the feed side and permeate side. So the driving force of the temperature difference is you will make a vaporization in the bulk, in the boundary area of the bulk and the membrane surface. Then when the vapor is transported to cross the hydrophobic membrane, and in the permeate side, due to the low temperature, the condensation is happening. So if you want to collect the water, the water will change the phase from the liquid to the vapor, and the vapor crosses the membrane, and then the condensed here. And then why ammonia? Because like water, you can turn the ammonia phase from the liquid to the gas phase. And the key point is you need to understand this ammonia chemistry. I think you have learned from the high school. Okay. So when we looking at this ammonia chemistry, right, and the depends on the pH value, right? So ammonia in the liquid phase at the lower pH, and when you increase the pH, this ammonia will vaporize and turn into the gas phases. So our group has been working on membrane distillation over the last 10 years. So we start to make a hydrophobic membrane and understand this mechanism and also apply in the resource recovery. So our first study of this ammonia resource recovery that we published in 2019. And then we now also expand our membrane distillation application into water and energy aspect. And we have made quite over 50 publications in the membrane distillation area. All right. So in order to increase the ammonia recovery, right, so based on this chemistry, we can understand that we need to have a higher vapor gradient of the ammonia, right? So the one key factor is the temperature, okay, and the other factor is the pH. So when you look at these factors, all are costly. In order to increase your pH, you need to add a chemical. So in order to add the temperature, in order to increase the temperature, we need to have a heat source. Okay. So I think this morning, Dr. Lu or Professor Lu also introduced kind of the concept of circular economy, and when we invent or introduce some new technology, right? So sometimes new technology can be not necessarily easily cheap, but we need to optimize. So always you need to look at So what is the added additional cost, and also how this additional cost will bring the greater value so that you can offset your cost to make a more greener and sustainable solution. So the concept is, as I explained, is quite simple. That this hydrocarbon membrane and ammonia will cross vaporize, and then when you circulate sulfuric acid, it's really so this is like a pH increase and pH decrease. Okay? And actually, this concept has been published in many papers. So in our earlier study, we tried to understand how this mesh and heat transfer is happening across the membrane. Actually, we make kind of vacuum membrane and understand the pH effect and also temperature effect. Okay, so now, so still this is an ongoing process, so the data is not completed, but I just want to share the progress of our study. So we try to first stage, we employ this hollow fiber membrane. The reason is because hollow fiber membrane can have a large membrane surface area, so that it can increase the recovery rate. And also why you are asking why 2 stages? Because the first stage will be kind of buffer, because when you deal with wastewater, volume is one of the issues. So the first stage, we try to increase the ammonia recovery, okay? And then we again use the simple sulfuric acid circulation, and then collect ammonium sulfate. And then second stage, because this collected ammonium sulfate is the free from wastewater, okay, and most of organic and other those found in contaminant are removed in the first stage. So second stage, we directly use ammonium sulfate to collect the pure ammonia gas in the ammonium solution, and then we have a downstream process with collaborate with the other scholar to break this ammonia to convert ammonia pure cell. Okay. All right. So this is our proposed idea to our government, and then from the anaerobic digesters. So we have a first stage of the hollow fiber. So then this ammonium sulfate can be used for fertilizer or can be feed for the next stage. But unfortunately, because Hong Kong, we don't have any agricultural industry, so this fertilizer is low value. So instead of using this, as a fertilizer, we will use this as a feed to the next stage, and then collect this pure ammonia gas or a solution. Okay, so this is the idea. So we have now working on this optimization. Of course, in the higher pH it's better, and also the temperature also can help to create the vapor pressure differences, and also the feed flow is not very rapid pollution factor. So after we run all this the first stage, we try to now the optimizations. Okay, and compared to the hollow fiber and the plastic one, and in terms of removal efficiency, the hollow fiber is much better because of high packing densities and also the large surface area. Okay, so this is very simple. Our second stage test that we collect from the very high concentrated ammonium sulfate. We collect this ammonium gas. Well, still we don't have very complete data, but we are now collecting with we collect ammonia gas, and then process the cracker, and then we will produce this the energy. Okay, so this is also one of our government project with the Hong Kong Political University. And then the other project is we combine this ammonium, the membrane distillation, because after the second stage, what you get is ammonia gas or ammonia solution and pure water. So the ammonia can be used as a fuel source, and the water can be also integrated with the electrolyzers, okay, to produce hydrogen. So this all 3 project is we just start early this year, and hopefully so the first ammonia production study is almost done, and the second study connected with Anna's part. I think hopefully I can share with you when we have a simple data. Okay, so the first part is a more practical application, and the second study is one of my PhD students' work. That during this study, my students proposed that, okay, so instead of controlling pH, what if we combine electrolysis, then we can concurrently increase the pH, and then help us to generate the ammonia vaporization. So actually, the idea is very simple. You create this anode and cathode. So this is again like electrochemical membrane distillation concept. That your water will be split to the water and OH ion, and then on the surface of this cathode, which we made the CNT layer, then due to this OH ion, the pH will be increased. Okay? So once this pH increase, this ammonium ion will be vaporized ammonium gas and then cross the membrane. Okay? So this is just the using this electrochemical assisted way to naturally increase the pH and also induce this ammonia recoveries. So as I explained, the concept is simple, that we combine this ammonium equilibrium at the pH and also water splitting in the electrolysis. Combine this one to concurrently increase the water pH and generate the ammonium gas, the ammonium recovery. So this is our simple cell. Okay, you can see here that the this is the anode, and the cathode is the CNT, multiple CNT. So how to optimize this process is we control the coating density, because you have a higher current density. That means you can increase the pH more easily. So higher coating density and higher current density is the key point. But of course, we have to also look at the optimization, because if we increase the current density too much, instead of always, you will also have a hydrogen derivation too. Okay. Because the pH is very important, we also add a sensor of this pH probe on the surface of the CNT, so that actually you can control your pH increase by controlling this coating density and current density. Okay. Yes, so the higher coating density, higher conductivity, and also the less power. So in the end, we need to calculate what is the power consumption. So power consumption is also depends is proportional to your current density. So you need to understand that what is the ammonia recovery per applied current density to calculate your power consumption. Surprisingly, compared to literature, so this ammonia removal efficiency is relatively high compared to the literature. So what the literature introduces, they use carbon cloth and also some other material. And you can see that we have achieved depends on the temperatures and also depends on current density. The highest amount is about 600 grams of ammonia per meter square per day. So then now we are now working on the mechanism study. Okay, so to summarize, so we know the ammonia is the high demanded chemicals, and also the production require very significant energy. And this creates a lot of environmental challenges, because uncontrolled ammonia discharge in water and wastewater pose the serious environmental issues. So we believe the membrane distillation process can be effective method, one innovative way for simultaneously removing and recovering ammonia from the wastewater. So integrated two-stage system can be practical for the control to concentrations and then recover high and pure ammonia or ammonia solution from the sludge digestate and transform it into high value product. And the last but not least, so advanced electrochemical membrane system can also open up the opportunity without the chemical addition, so chemical-free ammonia recovery and minimize the pH fluctuation. So now we are also going to further investigate the effectiveness of this electrochemical membrane distillation system. So this is the end of my talk, and before I finish, so our group is now looking for young caliber. We have a postdoc opening, and also we have a research assistant professor opening, and also we are also looking for PhD candidate. So we do all. Thank you so much.
Professor Han, thank you for great presentation. We have two questions.
Questions?
Any question?
Thank you, Professor Han. Very good presentation. Just wondering, this ammonia is very toxic and very corrosive. So when you design like a little bit scale up, so do you think the MD and this weather this will create more problem of your scale up issue? Also, wetting of your membrane. Ammonia is not really a problem for the membrane wetting of MD. So what's your perspectives?
Okay, so the first question for the safety. So because when we do the lab scale, right, because we set the scale in the boom hood, so we just control. And of course when we scale up, so you know the scale up is very different from the lab scale. So now we also have the scale up is Apple and our unit in the real sewage real the wastewater treatment plant, and involve a lot of mechanical and safety issues. Of course, we need to go through all this safety regulation, and also we have to follow all this kind of guideline. So for the scale up is the next stage. So I haven't. And the second thing is the wetting. Well, yeah. So the lab scale is quite easy, and so we didn't. When you have a good the membranes of fixed functional radiation, the wetting was the short time was not issue, but of course always the challenges, the main question is what will happen under the long-term operations, and also how can we find the suitable membrane. So now we are testing commercial the hollow fiber and also the plastic one, and also we also compare our own membrane things, and also recently also when I met the those industry or the adapting membrane distance technologies, you know that these days those direct distillation, they actually concept is membrane distillation plus the electrolyzer, right? But they also cannot find a suitable membrane. They just use PVDF. So I think also I see some niche market there to develop the membrane for the application of water and energies. So
Thank
what is
you.
the experience that when you work with ammonia? So wetting is what
No,
was
I don't want to answer anything. I'm not a speaker.
Thank you very much, Professor Han. Very wonderful presentation. I'm just wondering with regard to your advanced electrochemical MD system.
Yeah.
Because we need at least around page 9 or 10 for volatile ammonia.
Right. Yeah.
And so the generation of the hydroxide ions there, so it increases the pH. But how do you control, because the starting pH of that water body, the feed water, how much is the starting pH usually? And when you increase up to 9 or 10, so you need to have a lot of recirculation, or one pass is enough for the pH to be at least 9?
So, you know, initially our wastewater pH is like 7A.
Okay, yeah.
So then, of course, when pH is below 9,
Yeah.
it won't happen.
Yes.
So you need to, at the minimum, you need to increase the pH at 9, whether you use a chemical or electric the lysis process.
Yeah.
So then here is you need to increase the current density. So which means you increase the current density to generate more OH ions.
Yes.
So the current density is a key issue. So that's why we actually add a pH sensor here.
Yeah.
Okay. So we add pH sensor here. We control the current density.
Yeah.
And also the current density also depends on the material.
Yeah.
So what we do is that we make a different coating density of the CNT on our cathode.
Yeah.
Okay, and then try to regulate the current density. Also, this is also depends on your voltage.
Yeah.
we provide the coating density, current density, and voltage to find out the power consumption and then ammonia recovery to make us optimization. So now we are at this stage of
Okay,
optimization.
yeah.
So
Yeah.
basically, if you want to increase the pH, you need to increase the current density to stir the water, so that your water will be break down to the total oil, so they increase the pH.
But you need to still recirculate that
Correct,
one,
correct.
not the one pass
Not the one
thing.
pass, yeah.
Okay,
Yeah.
thank you. Yeah.
I'm sorry, we don't have enough time, so we need to move next.
Okay.
Yeah, yeah. So also we have prepared some plan for peanut.
Yeah, thank you very much.
Thank you very much.